We have two talks this session. The first one is by Chris Miller from the Georgia Institute of Technology. He's a mechanical engineering major, and his advisor is Min Zhou. He's a fourth year in the fellowship. He did his practicum at Lawrence Livermore National Lab in 2016, and a second one at Sandia National Lab in New Mexico in 2018. And his title of his presentation today is Effects of Microstructure and Chemistry on Ignition Sensitivity of Polymer-Bonded Explosives Under Shock Loading. So, take it away.
Testing, all right. Well, thank you for the introduction. Said I'm the other Chris, and I'm glad that mine is the first talk after lunch, so if you need this for your power nap to get it in, I won't be offended, but I'm gonna do everything in my power to make this as exciting as possible. So, first off, to start out, on a lot of my thesis work, let's start with the context a little bit here. So the question is, what are high explosives? I'm working polymer-bonded explosives, and you always hear this term HE, or high explosives, come up. And what do we mean by that when we say that? We're specifically talking to an explosive material that you can shock in some way that basically a shock wave propagates through the material and a detonation starts to form behind it. This detonation moves at basically a supersonic speed that eventually overtakes the shock front. You get a full-blown detonation as opposed to some kind of flame front propagated by deflagration. So it's used in any number of things, solid rocket propellants, insensitive munitions, stuff like that. And certainly explosives and nuclear weapons to tie this all back to the stockpile stewardship mantra here. But if you're wondering why do we care that much about shock physics in particular, there's a little history lesson for you. In about 1966, there was a plane crash off the coast of Spain. I believe there was a refueling incident that was carrying some type of nuclear material. Crashed in the water, that's as much of a shock as you're going to get almost anywhere, in nature at least. So needless to say, this thing ended up detonating, didn't look very good, and we decided as a country that says, man, we got to figure out how to make sure that doesn't happen. What's the mantra? You know, it never goes off unless you absolutely positively 100% need it to go off. So we really like this idea of creating an insensitive high explosive. But of course, in order to do this, you got to understand exactly what we're working with here. So the focus of this, one of the things I'm working with here is this polymer-bonded explosive, or PBX for short. So it's really made up of about 2 or 3 different components here. First off, you have some kind of explosive grains or crystals. In this case, for example, I'm using a thing called HMX. It's a high melting explosive, and this is really the part, it makes up the majority of your explosive, generally speaking. And this is the part where initiation and ignition is going to start and happen. You also have a binder, usually on the order of 5 to 10%, maybe less, maybe more volume fraction, and this is really to hold everything together. And occasionally you might see some additives added in. For example, one of the things we'll be talking about here is what happens if you add in little aluminum particles, and how does that, basically, how does the microstructure affect the performance of this explosive? So this is all happening on, people study these things on a range of scales. You have what Brooklyn was talking about earlier with, MD simulations, granted not explosives, but people do that for this. Other people look at continuum. I'm falling right in the middle of what's called the mesoscale region. So we're talking about distances really ranging from, say, microns to millimeters and that kind of scale. So we're really looking at grain level stuff. So very just quick overview, how do these PBX detonate? Well, first of all, you gotta, and with the way I'm interested, you gotta impact it somehow. This could be flyer driven or laser driven. Basically, you take a really thin plate, you launch it at railgun type velocities, this is kilometers per second, or depending on how fast you're trying to model it. Or laser driven, you shine a bright laser material into a material which expands very quickly, which sends a shock wave through the material. There's gotta be some kind of mechanical dissipation. I'm a mechanical engineer, so this is my strong suit. And because of that, things have a tendency to break down in one way or the other. This is pores collapsing in on themselves. This is fractures starting. This is every possible way you can imagine to break something tends to happen at high velocities here. Or plastic flow, the material just overall bulk deforms past its elastic limit. All of this, if anyone who has ever taken a thermodynamics class, of course, probably knows, you say, man, all this energy, where did it go? 90% of the time, your answer is going to be temperature, which is really no different here. So all of this mechanical dissipation ends up with a rise in temperature, which creates these hotspots. And hotspots in this context is a very localized temperature spike in a region. So sometimes you might not be worried about, it's really like, what is the point of failure of the material? Because that one rise in temperature can start a chain reaction of chemistry that goes on to produce a detonation wave. and so on and so forth. There's just a little picture here of somebody, for example, modeling as a shock wave goes through a single, for example, void here and how it kind of collapses and what happens with the material. You'll notice this looks very much like fluids because a lot of these are done using hydrodynamic codes, which basically takes a solid material and under high enough pressures, it's close enough to a viscous liquid that that's how you're going to try to model it. I kind of mentioned very quickly some key ways these hotspots develop. There's mechanical failure here. There's defects in the microstructure. Perhaps when you create your microstructure, there are already voids. There are already debonding sites where the polymer and this grain aren't exactly touching each other like you had hoped. Nothing's perfect. And it's my job as a mechanical engineer to quantify and see what can we tell about that information that's not perfect and possibly how to make it better, or at least more tailored. So I'm a computational person, so I apologize if you're an experimentalist, but you're gonna have to deal with me for the rest of this presentation here. So I like to deal in the realm of this ideal world in which everything's perfect and all the physics works exactly as a program and says it should, which is not how any experimentalist ever views the world because you're right. But sticking with me, this is one of the few times you're gonna be like, yeah, I have a lot of respect for experimentalists, and I realize that it's really difficult, which is why I took the easy way. So we take some of these real samples people can generate, and it's my goal to basically take this and transform it into some kind of idealized microstructure. And from here we can put in certain defects we're interested in, maybe voids, maybe cracks, maybe other things. We run it through basically our own in-home built lab code. We call it Codex because we got to have an acronym that sounds cool. It stands for Cohesive Dynamics of Explosives, because when you can't come up with a cool acronym, you start adding in multiple letters for a single word. Not sure what the rules are on that. But we end up with these like temperature fields here, and then we go through a whole post-processing, analyze it to basically get realistic engineering data we can kind of feed back to experiments to help basically further or refine the direction of experiments. So this is kind of a big overall picture of what we're going to be looking at. So some types of microstructure we'll look at here. Again, we're looking at some things like cracking, debonding, any of these heterogeneities that tend to happen. For example, you say there's a PBX here, it's a aluminized PBX, you got these like big, large micron size, 250 micron size grains going on here with a bunch of tiny little aluminum particles. One of the reasons we're interested in aluminum in particular is because it actually works as a desensitizing agent. When you think about really, really fine aluminum shavings, they have a tendency to burn very well, but they don't initiate. They're not just going to explode out of the blue. So it's kind of like adding fuel to a fire, but reducing the number of grains by replacing them to basically have a method to keep the strength of your explosive for whatever you need it for, but decrease the chances of it igniting and going off. So how do we go through all of this? Honestly, there's a lot of work that goes into this that I'm not going to bore you with. You can imagine the blood, sweat, and tears of years and years of grad students goes into developing this Fortran 90 code. Yeah, and also if you rolled your eyes when I said Fortran 90, believe me, you get used to it over time, I swear. And so we developed basically this cohesive finite element model. This is a Lagrangian framework for those of you who are not computational people. This is basically a model where you generate the microstructure you're interested here, and then you mesh it. And as your material deforms, your mesh deforms with it. It's very good for solid mechanics. It's a bit more accurate. Does have a tendency to run into problems when you deform it too much, but we'll get into that later. So we can basically do a cohesive finite element. What this means, if you're clever, you take these normal bulk elements that you see in a finite element, but you insert basically an element with zero area in between. The nice thing about this is, so it's really nothing is in between it, but you can still assign it material properties, i.e. strength, how much energy is going to take to break these, to fracture them. And so because of this, you end up with this nice arbitrary crack propagation. This is not a model where you say, yeah, our cracks are going to form in this location. Basically, we can tailor this to a critical fracture energy level and basically just let the code run as it is. Here, by the way, what we're seeing when I'm modeling is this aluminized PBX. Green is your HMX grains, your crystal grains. Red, tiny pieces, if you have good eyes, you can see it is your aluminum particles. And everywhere else that's blue is this binder, this Estane binder, kind of holding everything together for this example. So we run through our code and we get these nice, fun little images to play. But what we're looking at here is basically at a relatively high flyer velocity, we're imposing what's called the piston velocity here at the top. So basically we're just hitting this at a constant 500 meters per second, you can kind of see how the stress wave propagates through and eventually attenuates here. But more importantly, we take a look at all this residual temperature that's left behind. So using that temperature, what we can do, we can analyze. If you look at it closely, you'll see there's lots of kind of residual heat that's remaining on the borders, on the boundaries of these. And so the question is, how do we translate this to the sensitivity of the material? Well, what we can do, there's a fellow named Craig Tarver. You may have heard of him if you're familiar with the shock physics community. He's basically done a idealized model of what does the size and temperature of these hotspots have to be to achieve what they call criticality. Because the hotter it is, the more likely it's going to blow up. The larger it is, the more likely it's going to blow up. And how does that trade off? So we basically look through every single point here where we have a temperature spike. And just for simplicity, we break it down to a single one here. And we kind of cut through it like contours. And as we do, we say, all right, here it's pretty big, but it's not that hot. Here it's a little bit smaller, but it's hotter. And we plot this whole thing over time. And basically, we just compare it to this threshold to say, again, computationally, in an idealized world, it's reached the point of no return. It will grow to detonation at some point. Using all this information, we can kind of plot out theoretically how should this material behave. So what we're plotting here is power flux on the x-axis, energy fluence on the y-axis. So you can think of this kind of like almost equivalent to how hard are you hitting this material and what's your total energy, which is based on how hard you're hitting it and also what's like the thickness of the flyer that you're impacting this thing with. And I did it, for example, with 4 different types of aluminum, 0, 6, 10, 18%. And so what you see is it decreases here, which means that for an increased amount of aluminum, you're starting to need a thicker and thicker flyer for the same velocities to try to get it to reach this criticality point. So you're seeing this desensitized factor that we know from experiments to be true, so which is kind of nice. Down here, you can kind of see, ignoring necessarily the J-parameter, but I can get into that later. This is really just showing that what is the spread of your data around these Fitts line. This is called we call it a Hugh James plot. It was first done by Hugh James, a shock physicist. And anyways, it's a good way of kind of measuring sensitivity. So we can kind of use this information to say, all right, what about the microstructure? Because we're running through this code, we have all this information saved somewhere. What about this code can we use to figure out what exactly is going on? It's desensitizing. Why is that the case? Well, what we do is we say, all right, well, what's our heat density? It's a little bit less for adding aluminum, so less heat is generated, but why is that the case? Interestingly enough, if you look at this kind of bulk plastic work, no matter how fast you're hitting this, it's roughly equivalent, but that's not the case for this kind of localized frictional work. And what this means is that it's really the very localized friction that we're seeing, which is as soon as you send energy through, the shock wave, cracks generate, they rub against each other, generates heat, and that leads to these critical hotspots. So it's kind of nice to kind of break this down. This is just a little bit more of an analysis of this, if you will. So you got 0, 10, 18%. We're seeing that basically as you hit this, no matter how much aluminum you have in, you have the set number of cracks. There's a certain crack density you're achieving. But when you actually normalize it to the amount of aluminum, what you're seeing is that even though they have the same number of cracks, it's tending to follow the outlines of aluminum. Basically, the bonding energy between the aluminum and this matrix surrounding it is weak enough that you think about it, if your crack's going through, it hits a wall of aluminum, it's going to go around it. And every crack that spends the energy to do that is one less crack that's potentially going into the energetic crystal, the HMX. So we don't particularly care if the aluminum heats up because that's not really what starts this whole process. I did a brief little study comparing different aluminum sizes. And again, the smaller you make the aluminum, the greater surface area you have. And so you start to see, again, more of this desensitizing effect when you have a very, very smaller aluminum particles. Now, everything I just talked about is nice, and I like it. Of course, that's why I did it. But I'm specifically leaving out, we haven't considered the actual real chemistry yet. We're just saying it gets to a point, and then theoretically it should work. But how do we handle that? I'm also not talking about pores. How do we handle that collapse? Well, if you're like me, you sit there and you kind of bang your head against the wall trying to figure it out, and then you're lucky enough to remember that you're an SSGF fellow, and you say, wait a minute, we can go to one of these national labs. They have some of the great codes to work with this. So I begged and pleaded for a bit to, I ended up going to San Diego National Labs and found a couple of researchers out there brave enough to take me on and let me mess with their code. It's called CTH. It's an Eulerian-based hydrocode. Again, for those of you computational people, unlike Lagrangian, where you have this mesh that deforms as the material deforms, Eulerian really treats it as like a liquid, so your mesh stays constant, material flows into and out of it as needs be. So using this, I say, all right, well, can we do something similar, for example, but let's do it with different code. So it's just really, you're trying to solve a different problem now. You need the best tool for the job, and no single code is going to do this. So what I did, again, I generated, now this is actually not technically a polymer-bonded explosive, it's just pure 100% packed crystals together, assuming there's no empty space. And I kind of modeled 4 different cases. I said, all right, let's just make a single literal rectangular block. Let's have one where we just put in holes, certain voids, about 50 microns here. Let's have one where we actually take the time to model this granular microstructure and put it in. And then we'll have a 4th case where we do both. So we can kind of run all these and have comparisons about what are the relative effects. Now, for those of you familiar with Eulerian hydrocodes, if you have a bunch of the exact same material next to each other, it doesn't matter how you define this, it still sees as one big material. So to get around this, we have gone out of our way to assign each of these basically a different little density. Normally HMX is about 1.9 roughly grams per cubic centimeter. But we basically had a variation of like plus or minus 30% that we calibrated. So your density may end up being 70% of what it normally is, or 130%. And if you're like me, you say, what are you talking about? What is 130% density? Relax, we've thought about it, don't get me wrong. This is kind of a very abstract way almost of accounting for certain heterogeneities that you see in the material that you're not explicitly modeling, i.e. voids that are too small for this, or perhaps you're looking at nano-sized cracks that you can't explicitly resolve. So we take all this material here. Quick background, we're using a history variable reactive burn chemistry model, which is exclusively, it's a convenient, albeit simplified, pressure-based chemistry model, and we're using this to basically simulate this detonation. And also, if you're curious of me, Grunheisen equation of state and a simplified SGL model that was calibrated by the fellows I worked with, Drs. Cole Yarrington and David Cattell at Sandia National Labs. And we take all this and we do a little bit of homework because you can't ever get away from this. If you're going to be a computational person, you got to put in the effort. You got to do a mesh resolution. You got to do a sample size test to discover really what is a good RVE or representative volume element. It's enough to make sure that, all right, it's good enough resolved for the purposes we're considering. And we're considering 2 things in these simulations here. One is going to be what is the shock pressure? As you apply this shock, you have a certain shock pressure going through. And something I'll tell you what it is in just the next slide is something called run distance or run distance to detonation. So we go through, we do all this, and this looks a bit different, you'll notice. Here, there's very much chemistry going on, and what we can do is, again, calculate this shock to detonation transition, or SDT. Not STD, that's very different. It took me a while to get my mind around saying that because it's a tongue twister. And so you can calculate this run distance. You'll see basically as a shock wave is propagating through material, eventually you have this detonation wave catch up. It eventually overtakes, say roughly, for example, this microstructure right around there. It's literally like you're standing there with a stopwatch saying, all right, who gets to detonation, a fully formed detonation wave first? Obviously, we can't do that, but we can with microstructures and computations because, hey, an idealized world, and that's the world I like to live in sometimes. But basically, the quicker you get to that point, the more sensitive the material is to ignition. It's literally like you're just reaching detonation quicker. So what we can do, we can model this and we can plot it in such a way that this is called a pop plot. So you take the pressure, how hard you hit it, versus how long does it take to get that point. Obviously, the harder you hit it, the shorter it goes, so this kind of makes sense. It's in a log scale here. The very first thing we tested is we looked at 0% voids, and then I started adding in about 5%, 10%, 20% voids. It's known that the higher the porosity of the material, generally speaking, the more sensitive it's going to come. So the fact that this whole line is shifting towards the bottom left indicates that we're at least agreeing with the general trends seen in experiments. So it's kind of like the very quick, let's make sure we're not crazy, nothing has gone terribly, terribly wrong at this point. We seem to be okay. Interestingly enough, we noticed that it's increasing or it's decreasing this run distance at a decreasing marginal rate, if that makes sense. So going from 0 to 5% is a pretty big shift, but then 5 to 10 and even 10 to 20 is much smaller. So there's going to reach a point, Of course, you can never have 100% voids. If you did, you're literally hitting nothing. So that can't ever be sensitive. That should be like way up here, it would be infinity, right? So this almost comes down to, at some point, there's got to be an optimization problem using this of what's really the amount of voids or porosity that you could use to better understand this and tailor this. So continuing on, again, I mentioned these kind of 4 microstructures we're looking at. One is homogeneous. One is just with that granular microstructure. There's a case with just 5% voids, what we're looking at, and there's a case with both. And the interesting thing you see here is that as you add in these heterogeneities, as you get farther and farther away from a very perfect system, you're much more likely to achieve detonation, which makes sense. There's imperfections, and as this wave hits the imperfection, material heats up. When material heats up, things tend to explode. So what you can see, nobody had really been able to characterize this, and again, this is kind of a first approach. People who are really into this will point out certain flaws with this, but this is a very good, easy way of trying to take something between, for example, voids and microstructure and basically generalize it to a macro scale. We got on time? All right, good. Hey, we'll make this work. So we go through, we do all this, we find that having the microstructure here, again, decreases it. And we could have stopped there, but then we thought, why not we do something clever? Which is, you got 2 types of people in this world. You got the people who say, oh man, look at the scatter in this data, oh, it doesn't fit well. Then you get people like me that says, there's scatter in the data, can we use that? So what we did says, basically it's really just fit to a power law here. So what we do is we just define this non-dimensional number, and it's literally taking a 2-dimensional space, and we're defining a value such that if you're on the best fit line, the value is 1. If you're above it, greater than 1. If you're below it, less than 1. Such that you can basically de-dimensionalize this down from 2D to 1D. And using that, we can basically fit it to just a general log normal cumulative distribution function here. And then because of this, we can just basically rewrite this into an actual probabilistic equation, which turns our single line of best fit into more of a Technicolor Dreamcoat looking thing here. So you get these probability maps, which is a little bit more useful from an engineering perspective, because you may not care, what's that exact point? Maybe you want to say, what is the point at which 70% of the time, if I hit it a certain, with a certain shock pressure, it's going to go off by a certain distance. So we can kind of, it's a little bit extrapolate data here, but we can generate these nice fields which give you an idea, not just necessarily of this actual engineering parameters, but also just what is the spread of this distribution here. Of course, you could stop there, but why stop there? What happens if probability, again, is your actual parameter? Here we're saying, given a pressure and a run distance, what's the probability? It's an equation, we can rearrange it, right? So what happens if you figure out, says, what's the pressure I need to get a certain probability for run distance? And then similarly, what is the run distance? How long of a sample am I gonna need if I know this needs to go off at least 90% of the time, or something such as that? So it's very useful in that engineering parameter. And overall, we did a very quick comparison with experiments. Again, the whole goal of this is to, in order to build this up to a very macroscopic level, I'm talking millimeters, there are a lot of people who will spend time and get bogged down a little bit in the physics, and you'll be 100% physically accurate at nanoscale, but maybe that's not the most useful. What if you could be 90% efficient, but have it way up to larger scales? Again, I feel I'm a little bit more of an engineer than a scientist sometimes, so I'm really curious about how can we use this to basically make a predictive simulation? So experimentals can come up to us, like we said, and we can run it through, and we can kind of give them ideas of what roughly will happen when we change individual aspects of this microstructure. And again, we could have stopped there, but what's better than 2D? The answer is one more D. So we can expand this to 3D. We can expand this to 3D here, and basically using basically the same concepts. Again, the idea is to take a real microstructure, you can scan it, create these idealized microstructures, shock it through, kind of measure these same things. Here we're inserting about 100,000 voids, give or take. Computationally, these are pretty expensive. They take a number of time. I run it on the Department of Defense supercomputer clusters. HPC is great, and I highly endorse giving them more money if any of you are in charge of that. So we can take this, we can run them through, and we end up with these kind of similar-esque videos. And the nice thing is, again, we're comparing this homogeneous voids, microstructure, voids. And if you look closely, you can really see, like, really cased with voids, for example, you see that it's not just this nice uniform case. There's really these individual void collapses and everything going on, and we can use this to tailor this information. Very quickly, we took 3D, and this is kind of the last major point I'll talk about. People say, do we need to do 3D? Obviously, the real world's 3D. We do lots of stuff in 2D because we don't have infinite amount of time. Nobody's been able to answer the question of say, well, is that good enough? So one of the things we do is we take our 3D simulation, we literally cut it in a piece, and we just run the exact like slice of that as a 2D, and we can kind of compare that as we do this. You notice it's a little bit different. It kind of varies based on where you'd expect, because you can't just compare a 2D to a 3D. That 2D has to be an exact slice of it. Otherwise, it's not exactly the same things you're testing. So overall, when you look at this, we actually, believe it or not, it's still a little bit preliminary. We're seeing pretty good agreement. But interestingly enough, 2D has a wider scatter range. So if you were to just pick a 2D range, it might not be, all right. It might not be the best. There's a little bit of scatter here. But last but not least, there's a very quick summary, but to me, more important of the summary is if you haven't listened to me by now, I highly doubt you're going to read the summary. So let's just very quickly, obviously, I couldn't have done any of this without the fellowship or the Krell Institute. I'd like to give them a big thank you. I get to simulate things exploding, and people pay me money to do that. And that's just the greatest experience I could have, plus the opportunity to go do not only one, but 2 practicums. I didn't have time to talk about the Lawrence Livermore one. Especially, but Dave Cattell and Cole Arrington were kind of my co-advised mentors at Sandia, and my lab mates for keeping me sane. And Brooklyn pointed out earlier, I think this is very important, I'm not actually, my lab mates aren't that freakishly short compared to me. I was standing on something down here. But we do have a life outside this. We're not always in the lab, and thank you so much.